Hi everyone, this is Aydin Sezgin from the University in Bochum, and I'm happy to welcome you to the tutorial on multi-tier computing and decentralized 6G communication networks at the VTC 2024 Spring in Singapore. I'm pleased to have this tutorial jointly with my colleagues Haitham Dakhrouch from the University of Sharjah and with the Robert Jeroen Reifert, who is also at the Ruhr University in Bochum. So without further delay, let's have a look at the overview of the tutorial. Here's now the overview of the content of the tutorial. After my introduction, we are going to give an overview of CRAN provisioning. This is then followed by the more general case of multi-cloud run-over provisioning. We are then going to look into details on hybrid cloud mobile edge computing. In particular, we are going to look into hybrid networks which utilize the concept of rate splitting, as well as systems which use extended reality device cooperation via cooperative NOMA. This is then followed by the discussion on AI-based robust computation and communication setups. And after this last technical section, we are going to discuss about future research directions and open questions. And then we are going to conclude the tutorial, and then I'm going to take your questions. The first part's introduction is going to given by me, Aydin Sezgin. The first section, introduction, is divided into several subsections, which is, first of all, the motivation on 6G and future network applications. Then we are going to talk about digital sustainability and energy efficiency. I will give an overview of mobile cellular networks, and then I'm going to motivate multi-tier computing architecture. As we are going to focus on 6G, it would be helpful to get an overview of the ongoing academic and industrial research projects on 6G. This is not a complete list by far. We are just going to mention a couple of projects. At the European level, there the flagship project HexaX2. There are projects like Reindeer and also the 6G flagship. Within Germany, we have the 6G research hubs such as 6GEM, 6G RIG, 6G Live, and Open 6G Hub, as well as several industrial 6G projects like 6G ANA. In North America, there is a NextG Alliance, basically, which is addressing several aspects of 6G. What we see here on the right is basically a vision of HexaX, basically, in which basically the human world, the physical world, and the digital worlds are basically connected with the fabric of 6G key enablers, among them basically connecting intelligence, network of networks, sustainability, global service coverage, extreme experience, and trustworthiness. Now, future networks involve many relevant consumer and industry use cases, such as augmented reality and virtual reality, such as industrial control systems, smart homes, as well as autonomous driving, smart cities, metaverse, and the digital twin. So the vision of the ITU on 6G is that it's supposed to provide an immersive experience, through the use cases of AR, VR, metaverse, and digital twins. That means we need to have low latency from a human perception perspective. We want to have ubiquitous coverage in cities, in homes, in several industrial regimes, but also while driving. That requires several concepts in terms of radio access techniques, as well as concepts which aim at robustness, at resilience, and reliability. And of course, the overarching goal should be that we are bridging the digital divide. That means we are connecting the unconnected and the underconnected areas. The vision also contains enhanced collaboration. That means the goal is to connect people, things, and places. Let's look at two use cases in more details. The use cases of digital twins and metaverse. First of all, digital twins are digital replications of physical objects or processes that act like the real-world counterpart, while the metaverse is a massively scaled and interoperable network of real-time rendered digital worlds. Now, if you look at the challenges, there are several challenges we have to address in those use cases. First of all, there's a sensitivity towards end-to-end latency. There's a challenge of providing computing as a service. We need to have ubiquitous connectivity. We need to have ultra high rates. We also have safety requirements and many more challenges to address. Is that there's a native support of AI and ML in the design of 6G, in the deployment, and in the operation of 6G. So that means we are going to have an AI native interface, ML-based research management, and so on. So essentially, it's expected that intelligence will be present in every part of the communication system to support the building of smart cities and communities as illustrated here. So 6G would then serve as an AI-enabling infrastructure which is capable of providing services for intelligent applications. And an AI-enabled interface along with distributed computing and intelligence would essentially and potentially allow for end-to-end AI applicability and the convergence of computing and communication. Furthermore, 6G is expected to be secure and resilient by design. So it means it should be able to continue the operation during disruptive events and quickly recover from disruptive events. It means it has to be robust and reliable to events, whether they are natural or man-made. As a foundational objective for all future technologies such as 6G, the United Nations defined as the Sustainable Development Goals, which are essentially a global blueprint and aiming at achieving a better and more sustainable future by 2030. There are 17 interconnected goals, and they are addressing pressing challenges such as poverty, inequality, climate change, and peace. And those goals, basically, which are interconnected, are seeking to balance social, economic, and environmental sustainability while protecting the planet. So regarding the sustainability of 6G, so we have borrowed this nice plot from Ericsson provided in a report from 2022, is referred to as breaking the energy curve. So in more details, what we see here is a total network energy consumption as a function of the network rollout over time. And what we see is that based on the rollout of a new generation of mobile communication systems, their overall energy consumption was increasing. So the idea is now that we basically cannot continue with business as usual, and we have to be able to, in essentially 6G, we have to be able to break this energy curve by using latest advances in technology, which then essentially enable energy-saving functionalities. And this will help us basically to reduce overall basically emissions of global energy caused by mobile networks, which are basically at 0.2% right now, and also the use of global electricity, which is at this point 0.6%. Globally. So an interesting fact is that the radio access network consumes most of the energy across the mobile network. Here's an overview of a typical mobile cellular network consisting of two main components, the backbone, such as the internet, and the cellular access network. The cellular access network consists also of two parts, the mobile core and the radio access network. The mobile core itself is a bundle of functionality that serves several purposes. For instance, it authenticates devices prior to attaching them to the network, or provides internet connectivity for both data and voice services. On the other end, the radio access network basically manages the radio resources. It means the spectrum, and makes sure that the spectrum is used efficiently and meets the quality or service or QoS for short requirements of every user. So as you can see, basically it corresponds to distributed collection of base stations. Yeah. So and it's supposed to basically serve the users which are considered to be mobile. Those users or user equipments were usually corresponding to mobile phones and tablets, but increasingly they can also include cars, drones, and even machines, robots, and many things. So in this tutorial, we focus on the radio access network within a multi-tier computing framework. Now, what is meant by multi-tier computing? The idea of multi-tier computing in the context of 6G refers to an architectural approach where computational tasks are distributed across multiple layers or tiers of computing resources. And the overall aim of the strategy is to optimize the performance, reduce the latency, enhance efficiency by leveraging essentially the strengths of different types of computing environments, like the cloud, the edge, and the sensors and controllers. So within the context of multi-tier computing, there are two computing approaches. The first one is cloud computing, in which the management of the resources is done in a centralized fashion at the central processor, and the CP is connected via fronthaul links to the base station. So the advantage is here that we have an improved coordination of the overall network. However, there are long propagation delays from the edge users to the CP and back. And since everything has been to be done centrally at the CP, that means we are ending up in a large-scale optimization. Furthermore, the fronthaul links are usually costly to deploy and are usually limited in capacity. So in contrast to this, we have the concept of mobile edge computing, where the base stations are basically also equipped with some processors, such that some computing can be done locally at the base station. So the edge processors are connected to the central processor by some coordination links, and this overall concept basically aims at reducing the latency and also to enhance the service quality. So the resource allocation is done in a distributed fashion, and this achieves basically overall in a cost-efficient, energy-saving resource allocation. However, there are strict constraints, particularly on both the power and the computation resources available at the edge, and of course at the central cloud as well. One of the major challenges in those networks is how to deal with cell edge users, as illustrated here, because they have often inferior service quality, such as very weak received power and strong adjacent network interference. One approach to deal with this is to provide mobile edge nodes, and that is illustrated here, because they have the advantage that they are flexible in the deployment, they can provide service on demand, and they can enhance the connectivity of the overall network. The challenge, of course, of those mobile edge nodes is that there are strict power constraints given by this, and one has to basically provide solutions for the mobility management. So this is now the end of the introduction. So if you have any questions, we might stop here and answer them, but you are free to write your questions in the chat, and we will try to answer those questions in parallel to the video lectures.